ورحمة الله وبركاته. الآن بنقدم ضيفتنا الدكتورة أسماء قديمات، وهي باحثة ما بعد الدكتوراه في العائدين ضمن جسر علوم ألماني فلسطيني، وأيضا المتحدثة عن مجموعة أبحاث العلوم النانوية لإلقاء ندوة بعنوان تجمعات الجسيمات النانوية، الترتيب حسب التنظيم الذاتي والمغناطيسية الجماعية Nanoparticle assemblies ordered by self-organization التي تعمل مركز يوريش الأبحاث، وأيضا تعاون مع جامعة كولن في ألمانيا. خذ أسماء، تفضلي. أهلا وسهلا.
Hello everybody, I hope all of you can hear me. So yes. Thanks Dr. Ayman for the nice introduction, and I would like to thank all who joined this seminar via Zoom. So I'm Asmaa Qdemat, and I decided and I thought it will be good if I divide my talk into 3 main sections. The first section I will give a brief introduction about myself, and which includes my work experience and my education background. Also in this section, I will briefly introduce where I'm working and highlight the main research that is going on in my institute. In the second section, I will move on to briefly highlight the main results obtained during my PhD research, which was done since 1.5 years. And the last section, I will briefly introduce the Nanoscience research cluster, which I created since 1 year. So, briefly, my profile, I can consider myself as a motivated and committed person. And as a scientist, I have a great ability of systematic and concentrated thinking. I believe that I will find an innovative and great solution for a challenge awaiting me in the future. To the languages that I speak, besides the Arabic language, I speak English and also German basics. And for anyone interested to contact me further for any comments or question, here you can see my contact information, the phone number, and my email address. One of the big achievements that that I'm proud of, that the creation of the Nanoscience Research Cluster since 1 year through the Palestinian German Science Bridge. So to my education background, I got my bachelor degree in physics from Al-Quds University in 2012. Then I continued to get my master degree in physics also from Al-Quds University, and my research was done at the Forschungszentrum Jülich Center for Neutron Scattering Institute, which was about ordering phenomena in magnetic nanoparticle assemblies, under the supervision of Professor Salman and Dr. Emmanuel Kanzina from GCNS2. After that, I continued to my PhD research also. I got it in physics from Forschungszentrum Jülich, GCNS2, and AVTA Aachen University, which was about nanoparticle assemblies ordered by self-organization and collective magnetism, which is I'm going to present later in the second section of my talk. My PhD was under supervision of Professor Thomas Brückel and Joachim Meyer from Oscar Center. So to my work experience, after I finished my PhD, I did my first postdoc position at Cologne University at the Department of Physical Chemistry Institute and under the with Sabrina Dish group. After that, I got my second postdoctoral position at Forschungszentrum Jülich Center for Neutron Scattering Institute through the returner program of the Palestinian German Science Bridge and via creation of the Nanoscience Research Cluster. So briefly, the technical skills that I have or I could get during my research. First, I have an experience using a high brilliance X-ray instruments, which called the Galaxy, and that I have to present later on. Several measurements that can be done at this instrument, like small angle X-ray scattering, grazing distance small angle X-ray scattering, X-ray reflectometry, and wide angle X-ray scattering. Also, for the magnetic properties, we have several instruments at my institute. And one of the main instruments that I'm working on is superconducting quantum user interface device, or what is called SQUID. By using this instrument, we can record the magnetization as a function of the field, or the magnetization as a temperature dependent. Also, I have an experience by using neutron instruments and using the large scale facilities. During my research, I had the chance to use Maria reflectometer, and where I performed polarized neutron reflectometry measurement there. Further details about this instrument will be described later. During my first postdoctoral position at Cologne, I had the chance to visit INL, Grenoble, France, and to perform polarized small angle neutron scattering measurement at D33 instrument. And also I had the chance to visit the synchrotron, where I performed small angle X-ray scattering under applying of magnetic field and X-ray photon correlation spectroscopy using P10 instrument at Petrograd. So where I work, as I mentioned before, I'm working at Forschungszentrum Jülich. Forschungszentrum Jülich is situated in the middle of the Citternisch forest in Jülich, Kreis Düren, Rhineland. Forschungszentrum Jülich almost covers an area of about 2.2 square kilometer, and it is a member of Holmes Association of German Research Center. And it is one of the largest interdisciplinary research centers in Europe. So Forschungszentrum, as we can see here, this is the map of the Forschungszentrum, where it contains two main entrances. Here as we can see the first main entrance, and here the second entrance. And here we can see also the nice lake, which is located in the middle, where we can find the cafeteria if someone visits this research center and need something to eat. And exactly, I'm working on the Forschungszentrum consists of 8 research institutes, and this research institute we have for advanced simulation, bio and geoscience, biological information, energy and climate research, neuroscience and medicine, and Jülich Center for Neutron Science, where I'm working, a nuclear physics institute, and Better Global Institute. So my institute is located exactly here behind the lake. So as I said, I'm working in Jülich, but during my work, I have to travel a lot, especially if I need the larger scale facilities. So I have to travel to a Neutron. And we have different neutron instruments. We have 13 instruments at Garching in Munich, MLZ reactor, and also we have some instruments at INL, Grenoble, France, especially IN12 and IN22D23. Triple X spectrometer, and also we have some instruments at SNS Spallation Neutron Source in Oak Ridge. So briefly about the research is going on in my institute, which is called Jülich Center for Neutron Scattering Institute, or Quantum Material and Collective Phenomena. In this institute, we are interested to develop and use a scattering method, both X-ray and neutron, to determine the structure and the magnetic order and excitation in novel quantum nano and functional material, in order to achieve an understanding of macroscopic properties and functionalities. So here we can see only a sketch that I try to summarize all the research is going on in my institute. And in GCNS2, there is a several institute, several research groups, each group interested in such a topic. And we have a group working in multifunctional material, where they are interested in to study multicalorics and complex oxide. Also, other group working in superconductivity and correlated electrons. Other research group focusing on quantum material, where they study vial semi-metal and topology and frustration. And we have also a magnetic nanoparticle group, where I came from, where we are interested to study the nanoparticle assemblies in monolayer or in mesocrystal multilayers. Also, we are interested to study the properties of single nanoparticle. There is also another group working on thin film heterostructure for spintronics application. So the facilities that are available in my institute, as I mentioned before, we have several research groups, And these groups focus in different research topics: film, nanoparticle, polysingle crystalline. In order to achieve our goals, we need to characterize our system, or we need to use different facilities. Such facilities are available in-house, and other facilities we have to travel to use it. So the in-house facilities, we have Galaxy instrument, which is X-ray, a high brilliance X-ray source, and also we have molecular Galaxy instrument, which is used for the growth of thin film structure. And we need also, for our characterization, so we need the microscopic technique, such transmission electron microscope, scanning electron microscope, and for this we have to do a collaboration with other institutes, which ERC Institute in Forschungszentrum. To use the large scale facilities for X-ray scattering, we use mainly DESY at Hamburg, and we use diamond and EC synchrotron. To use a Neutron, we have to travel either to Garching, as I mentioned before, Jülich, and also to use the Neutron at ILL or at ESS, or as I said, in SNS. And collective magnetism. So this section is structured as follows. First of all, I will give a brief introduction and general introduction about nanoparticle, self-assembly, nanostructure, and then to clarify why I was so motivated to carry out this research. Then I will give a brief description of the main characterization techniques that I used during my research and that I'm using up to now. After that, I will move to show the main results obtained, which I try to divide into three main topics. First topic will deal about the I will present a simple, cheap approach to produce a highly ordered monolayer of silicon nanoparticle, only using improved order by drop casting technique. And in the second main result, I will show the results of the 2D ordered array of ferromagnetic cobalt ferrite nanodots and how we could characterize this system using X-ray and the neutron. The third part of my talk will focus on directed self-assembly of magnetic nanoparticle on pattern substrate. After that, I will try to summarize the main point that I'm going to present, and then I will give a brief overview about the possible future work for my research. So I think nanoparticle word, it's a common word for most of you, but for people who don't know what we mean by nanoparticle. Nanoparticle is a particle defined as a small object that behaves as a whole unit with respect to its transport and properties. So according to the diameter, it is classified into three types. Either we call it ultrafine particle, which has a dimension 1 to 100 nanometer, or fine particles has a dimension 100 to 2.5 micrometer, or coarse particle has a dimension from 2.5 up to 10 micrometer. Now it is like the scientists, they could obtain a suspension of nanoparticle. It's possible since the interaction between the particle surface with the solvent is strong enough to overcome the density difference, which otherwise, if we could not overcome this density difference, we result in a material either sinking or floating in a liquid. So nowadays there is a several type of nanoparticle with different shape, with different sizes that we could collect it in a nice table, a periodic table, which is similar somehow to the element periodic table. And in order to achieve all these types of the nanoparticle and different shape, during the synthesis, we have to control several parameters. And this parameter, we could control the size, control shapes, composition, multifunctionality, surface modification, assembly. And one of the main parameters that I am interested in, or I was focusing on to study, is the shape of the nanoparticle. So according to the morphology or the shape of the particle, scientists usually have taken to name it after the real world shape that they might represent. So we can have like a nanosphere particle which has a spherical shape, also nanorods which has a rod shape, nanoboxes, and nanoneedles. Also, and more have appeared in the literature, such as the nanostars or also superpole particle that I studied during my first postdoc position at Cologne University that I'm going to present later. So now, after I finish the introduction about the nanoparticle, how we can get a nanostructure from this or fabricate a nanostructure or an ordered structure from this nanoparticle. Nanomaterial and its fabrication, it depends on the dimension. Either the nanoparticle, it has 0 dimension, which called like such as quantum dot tolerance or gold nanoparticle, nanoscale clusters, or 1 dimension, such as nanotubes, wires, rods, or 2 dimension, like thin film plates, layered structure, or nanomaterial, which I'm going to present later, and the 3D arrangements, such as like the bulk nanoparticle or polycrystalline. So there is several approaches to fabricate nanostructure, and the main techniques that we use, top-down approach or bottom-up approach. So top-down approach, so we started actually, this is a common approach, and we started from a big element, bulk material, and we cut it into to a smaller fragment until we reach the particles into the nanoscale regime. This method, it's not preferable for industry because we need an external tool to break this big particle, and this is actually which costs a lot. Therefore, it's not preferred. For this top-down method, such as the electron beam lithography or deposition. But for the bottom-up approach, we actually start with a very small particle, and we assembly method until we can produce a nanostructure. Top-down approach, as I said, such as electron beam lithography, and using electron beam lithography, we can end up with a nanoscale regime particle. So during my research, I had to prepare such pre-structured silicon substrate with a nanometer width groove. And briefly, what we did, we cleaned our silicon substrate, and then we used via spin coating. We put a resist, and then after that we exposed a specific region in the resist to remove via electron beam, and in the development step, which we remove only the places which was exposed to the electron beam. The second approach is a bottom-up approach, which is a very simple approach that we can use a simple assembly methods, such as drop casting, where in drop casting, as we can see here, it's a very easy preparation method. We use the wafer, and in my case, I use silicon wafer, and you have only to control the volume of the droplet, the concentration of your particle, and other parameters until you get your desired film. The second method that we use in the bottom-up approach is a spin coating method, where in this spin coating method, we use a special simple instrument called spin coater, and we mount our sample in this spin coater, where we have to control in this the rotation speed and the rotation time. And once we mount the sample in the spin coater, we deposit our particle above the wafer. Until the solvent evaporates. So for the third preparation method, I use dip coating, which is a very simple and easy preparation method. We have to care about the concentration of the particle, withdraw time of the substrate. It's the idea behind it. Only we deposit our substrate, or we dip our substrate inside the nanoparticle suspension solvent, and depending on your desired film or desired coil, you can control how the time that it is the substrate inside the suspension and the withdrawal time. So now I will move to the self-assembly. Self-assembly is a very to understand self-assembly in easy way and in a direct way. We have to understand it. Like if we just think that we have a Lego bricks or kits, and then by this we can actually build such a structure, either 2D or 3D or non-uniform structure. To compare it to nanoparticle, so some scientists, they define self-assembly is a spontaneous organization of molecules or objects into a well-defined aggregates via non-covalent interaction. Okay, that's mean, so the nanostructure, there should be some interaction that control the self-assembly of our particle. Other group or other scientists define it as a group of components interacts with each other. Like if we have, and which become, if we have a less order component, then become more order component via some interaction forces. The information that is coded in a single nanoparticle or in a single particle, it defined later on determine the interaction between these particles. The component interacts with one with each other through a balance of attractive and repulsive interaction, and these interactions are generally weak compared to the thermal energy. So in order to adjust the position of this particle within an assembly, once it has formed, interaction must be reversible, and sometimes we have to use templates are often employed to improve order and perfection. We call it in this case directed self-assembly that I'm going to explain at the end of this section. As we can see here in this plot, that we have to use such a templates and deposit our particle in these templates in order to achieve our desired nanostructure. So, nanoparticles, why the research with nanoparticle, or I'm interested to work with nanoparticle. Nanoparticle with different shapes such as a cube or a sphere serve as a building blocks for atom or to form nanoparticle superlattice. Also, I'm interested with nanoparticle due to the potential application in various nanotechnological application. And mainly, I'm specifically interested in monodisperse magnetic nanoparticle because it's a promising candidate to increase the magnetic density, the density of magnetic storage devices to terabyte per inch square. Besides this, also even the magnetic, but the magnetic interaction between nanoparticle is still not well known, and it's becoming an important parameter that we need to understand and well control. Therefore, I'm interested in that, as also to a matter of fact that only the magnetic interaction in bulk between atoms in bulk, it's a well-known direct and indirect exchange coupling, but it's not known in between nanoparticle. And to my knowledge, only this magnetic interaction is studied for using macroscopic magnetization techniques, and only for particle assemblies showing a short or a short range order. So, as I said, I'm interested for this to understand the magnetic interaction between the nanoparticle, that which leads to a desired structure at the end. And one of these interactions, which is the magnetic dipole interaction, which only also depends on the orientation of the magnetic moments and also the relative distances. So the main, what I studied exactly. So the main focus of my research was to build a highly ordered two-dimensional and three-dimensional arrangement of nanoparticle, and then to study its structural and the magnetic correlation of this system using several scattering technique, using several characterization technique where the scattering, X-ray, and the neutron play a major role. So the application of the nanoparticle, it's an interesting and exciting topic, but only it's a one side of the coin. The flip side of the coin, that the ability to characterize such system or to find a suitable technique that provide us with the novel properties of this nano structure system in the nanometer regime. In order to reach a high coherence of the literal order of the nanoparticle, I use what is called the template, or in my case, I use the groove silicon grating, and I use this grating because it's suitable as a template for assisted self-assembly of nanoparticle. Now, briefly, the main characterization techniques that I use during my study. First, I use X-ray methods at grazing incidence. Two measurements performed, X-ray reflectometry and grazing incidence small angle X-ray scattering. Both measurements performed at Galaxy that I'm going to present in the next slides. And both techniques are a surface-sensitive scattering technique, which I use to characterize thin film, monolayer, multi-layer system. And the setup of both techniques almost similar. If we have an incident X-ray beam with K initial and directed toward the sample surface. In the case of X-ray reflectometry, the scatter beam is scattered at the same scattering angle equal to the incident angle, and we collect information as a function of the Z component. While in the GSACs, the scattered beam, the incident beam is scattered along K final and with an scattered angle alpha F and 2 theta final. The Z-axis is the normal to the surface, while the X-axis is the parallel to the direct beam, and Y-axis is the perpendicular one. So, in X-ray reflectometry, the scattered angle equals the incident angle, and it gives us information about the literally average density profile, the out-of-plane structure, and the layer thickness, interface roughness. But for GSACs technique, as I said, the scattered angle not equal to the incident angle, and we end up with the sum in plane component, where also in plane structural correlation, information about the bird object, object geometry, size distribution, and spatial correlation. So from GSACs, we can get inside information about lateral correlation from 1 nanometer to 100 micrometer, and for vertical correlation, we end up with 0.1 to 100 nanometer. So, from X-ray reflectometry, we can get information about the in-plane correlation to the surface, while from GSACs, the out-of-plane perpendicular to the surface. The other technique that I use or measurement is polarized in neutron reflectometry using polarized in neutron, and this was performed at Maria reflectometer, which done at which I'm going to explain later in the next slides. And from this technique, we can probe the depth dependence of the in-plane magnetization profile. So we can get insight to the internal magnetic properties of my particle film. The setup of this technique, if we have an applied magnetic field in this direction, and then if we have an incident neutron, either it is aligned parallel to the magnetic field or anti-parallel to the magnetic field, so spin down and spin up neutron directed toward the sample surface with an incident angle alpha I. This neutron either will get with the full polarized neutron, we can measure the four scattering cross section, which we call R++, R-, or called non-spin flip, which we are sensitive in this to the magnetization component parallel to the magnetic field. While for the spin flip scattering cross section R-, R+-, we are sensitive to the magnetization component perpendicular to the magnetic field. So as I said, measurement performed under a small angle or grazing instance done at Galaxy instrument at GCNS, which is a high brilliance laboratory small angle X-ray scattering instrument, and currently I'm working as a local contact for this instrument together with Emmanuel Kanzina. So here you can see a picture of this instrument, where this instrument is located exactly in 3 separated rooms. In the first room behind this wall, it's the X-ray source. We have a metal jet from Brückel X. Yeah. Yeah. Okay. So we have here the X-ray. We have a liquid metal jet along with gallium, indium selenide material. And if we have an electron beam with an energy around 70 keV hits the cathode material, then the X-ray will produce. So at the end, we have also what we have from this Then the X-ray, we have such a parabolic optics also in this room where the X-ray source is located, and the beam goes through this evacuated tube until it comes here to the sample chamber. Here we locate our sample, and here all this vacuum evacuated tubes up to the detector. We have one, it's a PALAST detector. And we can see that the sample, the Q range that we can obtain depending on the distance, sample detector distance that we can control through this tube via 5 steps. Also, this the detector distance is varied from 0.8 up to 3.5 meters. So the other instrument that I use, the Neutron instrument, as I said, Maria, to measure polarized neutron reflectometry, and it's a magnetic reflectometer situated in MLZ Gaussian beam unit with a high incident angle. So here we can see a real image of this instrument, or exactly for the sample position, where we have a hexapod and also a cryostat situated here around the sample in order to control the temperature. This instrument can measure polarized neutron reflectometry to obtain the out-of-plane structure. Also, we can perform grazing is a small angle neutron scattering measurement in order to achieve the magnetic lateral order of my system. Simply, the setup of this, we have, if we have the neutron came from the reactor and it is directed toward the neutron guide only, and then it goes through the velocity selector and the Fermi chamber, which is defined or decide when the neutron can start, and then we have a double reflection polarizer to polarize the neutron. After that, it directed toward the sample position, and then it will goes through the analyzer, which we have H3 cell, and we have the detector. It's the 2D sensitive PALAST detector. So from the Maria, we can apply magnetic field up to 1.3 Tesla and control the temperature from 4 Kelvin and up to room temperature 300 Kelvin. So by this, I will move to highlight the results obtained during my study. First, as I said, I will show a simple, fast approach to obtain highly ordered monolayer of silica nanoparticle, where also together in this part, I will show the main technique that I use to characterize my this monolayer. So in this part, I use silica nanoparticle, where this silica nanoparticle obtained by the collaboration with Johan Bottenhuis from ICS Institute, and this particle has a dimension around 50 nanometer, grafted with sterile around 2 nanometer in diameter and dispersed on fluid. So locally, this particle is characterized using several scattering, several microscopy technique. We use SEM, and also we use the transmission electron microscope. So from both images, we can see this particles have a regular spherical shape, and once it's deposited on the surface, tend to organize into two-dimensional hexagonal lattice. So to manually, I calculate the main diameter of this particle and the size distribution using the log normal size distribution, which we end with the particle around 49 nanometer and the size distribution less than 3%. Furthermore, I measured for this particle small angle X-ray scattering at galaxy in order to obtain statistical average information. And here we can see the SAX curve, which is intensity versus Q, which shows a very nice curve oscillation, which is an indication of a good monodispersed particle. The SAX data fitted assuming a spherical form factor, and we end up with diameter and the size distribution, which is somehow in a good match with the results obtained from the analysis of the SEM and the TEM images. So now I use this nanoparticle to produce the monolayer. So to prepare this monolayer first, to my knowledge, I was the first one who could obtain such a large homogeneous uniform monolayer over 1 × 1 centimeter square silicon wafer. So to produce this monolayer, I use the 3 preparation method. First method, which is only assembly drop casting method, and I only was controlling the volume of the droplet. And by this method, I end up with a part with a monolayer which is not uniform or homogeneous over the whole silicon wafer, and where some areas not covered with the particle, and some also there is a multi-layers, and some also with the grains, which comes maybe due to the surface tension, which leads to the contraction of the particle grains during the drying in. But somehow with this particle and with this good size distribution, we could find some good areas with some good degree of ordering. The second method I attempt to use sterile alcohol, and I thought this sterile alcohol will lead to improve the order between the nanoparticle and fill also the spaces between this between the cracks. But actually, what we end with a very nice the ordering between the nanoparticle become better than the one in the method one. But we end up with some domains having some domains oriented, separated by cracks, which came maybe due to the drying in, and having the same orientation. So in conclusion, the monolayer in method 2 is much better than the monolayer in method 1. Actually, what is the scenario behind the sterile alcohol is not easy to explain, as it's a complex, but as a speculation, maybe the precipitation of sterile alcohol take place on the particle or in the silicon wafer during the drying in. Also, maybe the drying of the edge of the droplet also playing a major role in improving the ordering between the nanoparticle or in the monolayer formation. This is only a speculation, and as the description of the monolayer formation is not an easy issue. In the third method I attempt to use the heat treatment method, and the idea was to put the monolayer obtained in method 2 in the oven, and actually to melt the sterile alcohol, and which lead to more free particles, and these free particles will lead to more order for further self-assembly. And via further self-assembly, we can solidify the ordered monolayer only by a minor change of the volume, which is actually the advantage behind not using which leads only to the minor change of the three monolayers at the same incident angle around 0.25 degree, and from the GSACs we can see similar features where a break routes along the QY in this direction obtained for the 3 pattern, which is an indication of the order of the nanoparticle, but the monolayer obtained in method 3, that this break routes is become more pronounced, which is an indication of the long range order. Furthermore, we observe these lines are along the QZ direction, which is due to the monolayer nature, and we observe some also diffuse rings which come due to the form factor of the single nanoparticle, spherical nanoparticle. But what we can see the difference that the break routes along QY in the monolayer method 3 is more obtained than method 1 and method 2. Also, this diffuse rings is become less, which is an indication that the most of the particles take place in the ordering, and the scattering from a single nanoparticle, it's strongly compressed. In order to compare all these GSAX patterns together, so it's easy to perform a horizontal line cut, which is done at this position exactly at the unity line, and from the horizontal line cut we can see that from the monolayer, the red line obtained in method 3, it's higher intense, which is due to the long range order. Indexing, I index the peak according to the assume 2D hexagonal lattice with a spherical particle size 50 nanometer, and I try to calculate the coherence length after taking the resolution of the galaxy instrument into account and fitting the first order peak by a Lorentzian profile, which gave me that for the nanoparticle for the monolayer in method 3 more than 480 nanometer, which is higher than the resolution of galaxy. It's around 500 nanometer. Now further, the pattern that obtained, the GSAX pattern obtained for this monolayer, I tried to simulate it using born-again software based on the store-born approximation. This born-again software is a free software that can anyone use for fitting and simulation of monolayer, multi-layers system, and they perform for GSAX or GSANS measurement. So to perform this, this software actually uses the physics of the store-born approximation, and in order to reproduce or fit the system, I assume that I have a monolayer of a nanoparticle, 2D hexagonal lattice, and we end out with the simulation part, which is somehow close to the experimental data. By comparing the horizontal section here, we can see around the unity line, we see that there is a good match between the experiment and the simulation. So by this actually, I would like to, in the first part of my research, and I could also emphasize or focus on that heat treatment together with some suitable additive with an melting point lower than that of the particle would be a good approach or good way to improve ordering between nanoparticle, monolayer, and multilayers. Then I will move on to the second part of my research, which focus on 2D ordered arrays of ferrimagnetic cobalt ferrite nanodots. Now I will deal with magnetic nanoparticle, and in this part I use the cobalt ferrite nanoparticle, which has a hemispherical nanoparticle. This sample obtained by a collaboration with Joseph Portali from Groningen University, Netherlands, and it has a dimension about diameter 24 nanometer and a height 10 nanometer. This cobalt ferrite, a bulk cobalt ferrite, it has an inverse spinel structure where, and it is a ferrimagnetic and have a magnetic, magnetic moment 3 newborn. Yeah. So the scanning here, we can see scanning electron microscope for this monolayer, and we see that almost has a regular spherical shape with some areas where is also some defects that we can't see any particle. I tried to analyze this scanning electron microscope manually to get the size and the size distribution of the particle, and we see here from the loop normal distribution that we have a particle around 24 nanometer with a size distribution around 8%. So in order to understand the out-of-plane ordering of this particle, X-ray reflectometry measurement performed, and we can see from the X-ray reflectometry that we obtained two different oscillations, where this big oscillation corresponds in the real space to the smaller thickness, which is our nanoparticle thickness in this case, and this small oscillation in real space is correspond to the large thickness, which is our oxide layer below, as we can see here, below our nanoparticle layer around 50 nanometer. For GSAX, we also performed GSAX for this to study the in-plane lateral order of the nanoparticle, and we obtained this Bragg rods along QY, which is due to the ordering between in-plane ordering between nanoparticle. The Bragg rods are indexed assuming the 2D hexagonal lattice. Also, we simulate the system using born-again software, and by assuming only a hemispherical shape of the particle, 2D hexagonal lattice, and with some random orientation of the domain, we end up with by comparing the horizontal line cut and the vertical line cut, we see that the vertical line cut, we are in a good matching. That means we are in a good expectation of the particle height or the nanoparticle, the layer thickness. Also, from the horizontal cut, we can see that some fluctuation or difference between the experiment and the simulation data which will come due to the inhomogeneous orientation of the domain, or the orientation of the inhomogeneous domain. Okay, so what we also performed, to study the magnetic properties of this nanodots, to the cobalt ferrite nanodots, we performed the magnetic measurements at SQUID, and I was interested to study the magnetic moment along any plane and perpendicular to the sample surface out of plane. So what I did, I measured magnetization as a function of temperature, as we call zero field cooling, and in zero field cooling first, in zero field cooling, we cool our sample from a higher temperature 400 Kelvin until 5 Kelvin in a zero field. Then we apply a magnetic field I applied 5 millitesla, and we heat it up from 5 to 400 while we're recording the magnetic moment. In field cooling, we cool it down from 400 to 5 Kelvin while the magnetic field is applied. So what we can see the difference between in plane and out of plane, that in plane we can see that reach here the point where we have the maxima of the zero field, we can obtain the bulk, the block temperature, whereas the temperature between the blocking state and the superparamagnetic state, and we see some decreasing in the field cooling, which is an indication of the magnetic interaction between the nanodots. For out of plane interaction, we can see that this zero field cooling, the green curve, we have some such a maxima here. It comes up due to the actually to the addition of the two sublattice of the cobalt ferrite nanodots, which ends up with such a high, and it occurs under a temperature called a composition temperature. For out of plane, we could not see any indication of a magnetic interaction, and here we can see the block temperature. After that, the particle goes to the superparamagnetic state, where all the particle spins oriented randomly. Also, we performed magnetization as a function of the field, and in both cases, actually here I forget to mention that in a plane it shows a magnetic moment higher than out of a plane, which is an indication that the particle is more energetically favorable to align along the field. The magnetization versus field, we perform two temperature, room temperature and 5 Kelvin, and for the in plane case, we in both cases in plane at the room temperature 5 Kelvin, it shows a superparamagnetic behavior, no hysteresis is affair, and also with Langevin function. And for out of a plane, we can see that at room temperature, it shows a superparamagnetic behavior with some very small hysteresis, as we can see here in the inset. And for the outer at 5 Kelvin, also shows superparamagnet with a very small hysteresis, and also an extra opening obtained at high and low field, which is due also to the net magnetization between the two sublattice of the cobalt ferrite and octahedrite. So furthermore, for this system, we perform polarized neutron reflectometry in order to study the magnetic depth profile, and this measurement were performed at at room temperature and two different field, at saturation field around 1.1 Tesla, and we measure half polarized neutron. And with this, we could not see any splitting between the spin up and spin down, which is an indication there is a splitting between spin up and spin down. Here, the red and the blue curve, which is an indication of a small in-plane magnetization component parallel to the magnetic field. By fitting this data, we end up with a magnetic moment equal 1.4 μ per formula unit, which is smaller than the bulk value, which is due to the frustration effect of the magnetic, the dipole interaction. And also, we could also, we calculate this magnetic moment using the SLD, magnetic SLD, and the nuclear SLD value. At terminus, we field around 0 Tesla. We measured the full polarized neutron reflectometry also in a plane, and we can see here the upper curve. It's the spin flip curve, and we see that there is no splitting between the spin flip, which is an indication that the complete randomness of the spin over the whole coherence volume, or to the zero net magnetization. Also, the non-spin flip, it shows no splitting, which is also come that my samples goes to the demagnetization state at zero field or at the remanence. This difference between spin flip and non-spin flip is due to the efficiency of the polarizer and the analyzer. We fitted the data and assuming a zero and it ends up with zero magnetic SLD, which is not surprising thing because at as we can see in this magnetization versus field, we see that the sample did not show any remanence at zero field, and which is actually which is not surprising them. But we can see here also the model that we assume to fit, it's not produced the data very well. It seems that we have some contribution, magnetic contribution coming in as the fitting does not reproduce the data very well. So that's we end at remanence our sample demagnetized state with zero net magnetization. By ending of this part, I would like to mention that it is possible to measure magnetic depth profile using polarized neutron reflectometry of monolayer of magnetic nanoparticle. So the last part of my results, which focus on 3D arrangement of nanoparticle, and here I use the magnetic. I use assemblies. It's grating lines of silicon. And it's play a major role in this part of my work. Therefore, I will start to characterize, show the result of characterization of these samples. It's produced by electron beam lithography by a collaboration with Helmholtz Nanoelectronic Facilities at Forschungszentrum Jülich, and we end up with the gratings groove with a width less than 100 nanometer. So from this, we in order to get information about the groove depth and the capping layer, silicon capping layer, we perform X-ray reflectometry, and we end up with two different oscillation, which comes due to the two different oxide layer that covering the two different depth profile. As you can, if it is clear from the scanning electron microscope, that we have here another also line. It's located between these two main lines. Also, we perform GSACs in order to study the literal periodicity of this grating, and we perform the measurement as the incident beam totally along the grating lines. And what we end up, which is we end up with this pattern, whereas diffraction spots appear along the semicircle, which is due to the intersection of evolved sphere with the grating truncation rods. This the radius of this semicircle is calculated as follows: as sample detector distance times the tangent of the incident angle. Furthermore, this pattern is actually sensitive to the accurate alignment of the direct beam along the lines. So further periodic orders we obtained, which is here due to the periodic structure, and the diffuse lines, which comes due to the roughness of the lines or sidewall angles, also due to the stitching machine of the electron beam lithography. After doing this intensity integration around this area, around the semicircle, we end up with this intensity integration, which shows only one fluctuation with two slope. Nanoparticle that I use, it's a superpole nanoparticle obtained from Sabrina Dish group from Cologne University, and it's a magnemite particle, a ferromagnetic, which has inverse spinel structure with vacancies. And this particle characterized using transmission electron microscope, we can see that this particle does not have any specific or shape. It's not exactly a cubic with defined edges, but some of them having some particle with a cube with surrounded edges. So in order to calculate the size and the size distribution, I did the analysis manually, and we obtained the particle size 14 nanometer and size distribution more than 7%. Further, to get information, global information or average statistical information about this particle, I performed small angle X-ray scattering measurement, and here we can see the Sachs curve. From the Sachs curve, I tried to fit it assuming different model, Korshel model, cube model, sphere model, superpole model, in order to exactly get the exact shape of the particle. And we can see here the Korshel particle is the orange one. Model, which is actually overestimate the first and the second minima, but for the second and third minima, while for the cube model, the green one, it's overestimate the second and the third one. Sphere model also, it's underestimate the first minima. While for the superpole model, the first one is to produce the data much better than the other form factors. That means we have a particle with a superpole shape. Now it's the time to introduce to you what do we mean by a superpole. Superpole, it's a geometric body that it's located between a cube and a sphere, which was the main research for me during my postdoctoral position at Cologne, and which is located between a perfect cube and a sphere. The equation that defines this body or this shape, it's defined as follows, where P is the parameter that defines the rounding of the edges. If we have a P, it goes to infinity, then we have a perfect cube with a defined edges, and equal when we end up with a sphere. So as also we did some simulation for such a shape, and here how it looks by assuming if we have P1, 1.52 and fair and infinity. So also to compare it with the perfectly cubic and the spherical form factor, we did some also simulation here, assuming we go from 1 up to 4, and we see that it is until we go to 4 that the first minima it goes up, and but for with 1 it's down, so with a perfect sphere. Now, after I characterize the nanoparticle and the grating lines of silicon wafer, I try to combine both together in order to obtain or towards a single crystalline 3D arrangement of nanoparticle. For this, I use a deep coating preparation method, and in order to study the system or the nanoparticle arrangement that I obtained, I performed X-ray reflectometry measurement, as we can here see, in order to see the out-of-plane ordering of the nanoparticle, which shows some oscillation which comes due to the nanoparticle layer inside this groove. Also, in order to get depth resolved lateral coherent structure of the nanoparticle, I performed GSAX. GSAX measurement performed in 3 different directions, as the beam along the lines and also perpendicular to the line and 45 degrees to the line. In all cases, it shows a strong modulation along the QY, which is coming due to the in-plane ordering of the nanoparticle, and the long QZ, which is actually due to the out-of-plane ordering of the nanoparticle. The measurements all performed at the same incident angle. What surprisingly is coming out that the position of these Bragg rods along the QY and the QZ is the same position as the beam perpendicular and 45 degree. What does this mean? It means no correlation between the structural and the arrangement of the nanoparticle and the geometry of the fringe pattern substrates. Now, this nanoparticle, to understand it better, we did a horizontal line cut and the vertical line cut. From the horizontal line cut, we can see all the peaks have the same position at the 3 different geometry, and we index that the particle according to 2D hexagonal lattice. That means our nanoparticle are arranged into 2D hexagonal lattice in a plane, and out of plane it's ordered into FCC structure, a stacking of hexagonal lattice where it's oriented along one direction. The last thing about this system, I try to study its magnetic properties, and again I perform zero field cooling, magnetization as a function of temperature, and magnetization as a function of the field. From magnetization as a function of the temperature in both directions along the lines and perpendicular to the lines, as we can see along the lines, it shows a magnetic moment higher than the perpendicular to the lines, which is an indication, or we have in a plane easy axis, that the particle is energetically favorable to align along the lines. And we can see also a decrease in the field cooling curve, which is due to the magnetic interaction between the nanoparticle, which we could not obtain in the perpendicular direction. For the magnetization as a function of the field, in both cases, in both orientation, at parallel and perpendicular at room temperature, we obtained a superparamagnetic behavior, and for at low temperature at 5 Kelvin, we obtained that both shows a superparamagnetic behavior, shows this hysteresis, and where also a super exchange bias obtained for the case for the in plane, as the hysteresis is moved toward the negative field. Okay, with this part, I would like to emphasize that the special confinement, mean directed self-assembly, could be a good approach to improve the order between nanoparticle if it's the wall width in commensurate with the particle size. Okay, now I will come to summarize the main points that I presented in my talk. So I show you how to obtain a highly ordered monolayer of magnetic and nanoparticle only using assembly drop casting method. And also in the second part, I show you how we could structurally characterize locally and globally, and also how we can magnetically characterize mesoscopically and macroscopically a 2D arrays of magnetic nanoparticle. And the third part, I focused on how we can obtain a 3D arrangement of a magnetic nanoparticle using a templated assisted self-assembly method. So as a future work, and already I started with it. So for the grating lines, as the only why we end up that there is no correlation between the grating lines and the arrangement of the nanoparticle, because up to now we could not understand the exact shape or geometry of these lines. Therefore, in order to understand this geometry, I'm trying now to full modeling the GSAX data of these lines using the semi-kinematic and dynamic theories, mostly by using the Stoddard approximation and Maxwell equation, and where I have to take into account several parameters like the solid wall angle from the depth, the top corner rounding, the line width, the line height, and other parameters. And then after that, the model will be implemented into the born again software. So, and then after that, the monolayer that I obtained in for silicon nanoparticle, also I started with this part, with this topic. I'm trying to use the method in order to obtain a monolayer of other several type of magnetic nanoparticle. And also this monolayer, I started also with this project that I'm going to use it as a template to deposit a magnetic thin film that I'm going to grow using the molecular beam epitaxy instrument at our institute. So the third part, this is after I succeed, I will try my best to obtain a single crystalline 3D arrangement of iron cubic nanoparticle, and then I'm going to investigate its magnetic ordering by grazing this a small angle, the scattering of polarized neutron, polarized GSAX. Then the simulation will be done by using born again software. So before I finish my talk, I would like to advertise this school that we have each year in our institute, which is the GCNS laboratory course in neutron scattering 2022, and this will be on from 5th to 16th September this year. Will be 2 weeks, 1 week at Jülich and the other week at the second week at Garching at the reactor doing some experiment. Also, the application is still open up to now, and it's directed actually for master PhD students as interested in physics, chemistry, material science, and bioscience. If anyone interested can visit this link or also can contact me. At the end, I would like to thank you all for your attention, and also I would like to thank all my colleagues at GCNS2 and all my collaborators. Thank you for your attention. Now, please, if you have any question for this part, before I move to present briefly the Nanoscience Research Cluster, feel free to ask me. Open your mic and ask me. Thank you.
Thank you very much, Asmaa. If anyone have any question. If there is no question, you can go to the second part.
What? Seems there is no question.
No question.
So I will move on to the second part of my talk quickly. Okay. So again, I just quickly, 5-10 minutes. As I said, I could create the Nanoscience Research Cluster since 1 year, and I would like actually to advertise this nano cluster for anyone interested to join it or anyone interested in the research that we are doing in this cluster. So I call it Nanoscience Research Cluster, which is actually between the Palestinian universities and German university plus Forschungszentrum Jülich. So the main objective of our cluster, of my cluster, was to connecting Palestinian and German scientists in the interdisciplinary field of nanoscience, or anyone who is interested in nanoscience. So the collaboration of my cluster based on actually it's full screen. Yeah. So to first doing to trust all the partners together and share our ideas together, exchange the information, the knowledge, and work as a team, assist each other, and then support each other. And the end, we by following all these rules, we can succeed and achieve our goals. So why I was only focusing, or was interested to build a cluster focusing on nanoscience? Because nanoscience or nanotechnology gained international visibility and become a leading research focus on the last decades. Also, the research interest of nanoparticle is intense nowadays because due to its nanoscale properties that can be introduced into uncountable new nanomaterial, and can be used in a wide range application of nanoparticle, either for a short-term application or for the long-term application. The fundamental aspects of this research cluster, we are focusing on fabrication, characterization, and applications. So objective of this nanoscience, as I said, the aspects. First, we are interested to develop of a novel nanoparticle. Therefore, in this research cluster, there are some scientists especially in the characterization, in the synthesis of this novel nanoparticle, and the other partners interested or experienced in characterization of this particle, and a tight collaboration between partners either in Palestine or in Germany. And the third objective or aspect of this cluster, to tight and repeated interaction between experimental and theoretical scientists, and also use of developed tool in medically relevant sensors means the application. So the requirement for this cluster, the requirement of my cluster was to a new generation of researchers highly skilled in or are specialists in advanced experimental technique, present theoretical method for developing novel tools and strategies in the field of nanotechnology. So the nanoscience cluster will address all these challenges that we are need by means we find the solution by using a highly interdisciplinary research through a dedicated team of chemists that will develop innovative nanoparticle and nanomaterial experimental biologists who will collect data from living specimens, and theoretical physicists and mathematics to interpret and integrate data into models. So the cluster network is shown as follows. So it contains of a research group, a group focusing on nanoparticle fabrication, as I said, in characterization and also in application. So here we can see the Palestinian side, and also from the Col University, and recently also Dresden University started in this started as a member in this cluster. So continuous interdisciplinary feedback. So what we need actually from you, we need a feedback, and collaboration will be essential for achievement with high relevance and for a long term or succeed for this cluster. The joint supervision of students introduced by PGSB also will tighten the scientific network. Early phase actually cluster plan, what we are planning, and we start to use the networking platform provided by PGSB, like workshops to advertise our cluster, and also to establish an intranet platform for a permanent information exchange, furthermore a staff exchange. Our expectation from this cluster, we expect that from this cluster we can end up with excellent career prospects to the fellows due to their combined training in an interdisciplinary program. Also, from this cluster, we can shape a new generation of young researchers that will no longer be hampered by the traditional boundaries of disciplines shaped centuries ago. And here we can see the participants of the nanoscience cluster according to their experience. So we have the participants, they are experienced in the nanoparticle fabrication, in the nanoparticle characterization, and the nanoparticle application from both sides, from Germany and from Palestine. The research infrastructure, what techniques that we, for the structural characterization that we need, we need actually for this, the Palestinian partners, they need the structure that they need for their research. microscopy techniques such as TEM, transmission electron microscope, high resolution transmission electron microscope, or scanning electron microscope, atomic force microscope, which is available, all these facilities in Forschungszentrum, and which give information about the size, morphology, and the crystal structure of the nanomaterial. Also, what they need, the scientists from Palestine X-ray based techniques such as XR diffraction, small angle X-ray scattering, which will provide us with characterization, the crystalline structure, nature of the phase, lattice parameter, and the crystalline grain size or the particle size distribution and shape. Also, what they need, the dynamic light scattering measurement in order to access the hydrodynamic size and for the detection of the agglomerates. Furthermore, what they need for the magnetic properties are the super magnetic quantum interface device, magnetometry, vibrating sample magnetometry, and by using this technique, they are aiming to measure the magnetic properties of the nanoscale material, record the magnetization versus field loops for the magnetic nanomaterial, and obtain parameters such as saturation magnetization, remanence magnetization for their system. Also, they need a polarized small angle neutron scattering technique, which to investigate the internal magnetic structure. Okay, these all the facilities that I showed it, which is available at Forschungszentrum Jülich, except the polarized small angle neutron scattering. And to access actually the neutron scattering experiment, we are planning to use, and we are using the facilities available in IL in Grenoble, France, or in MLZ Garching. Also, we are for the X-ray experiment, we are planning, we are using the DESI at Hamburg, and the plan for long term, we are planning to use the beam lines and the synchrotron light for experimental science and application in the Middle East, which is called CSEM. So here's some Nanoscience research cluster projects supported by PGSB. Some they are still in doing their research, and some who finished, like Mahmoud, who finished his master project and now recently started his PhD project. Also Hiba, who she finished her PhD, defended her PhD recently, and also Sam, who also started his PhD project recently, and other they will started soon. So the planned project through this cluster, we have exosomes in medical application, which is actually started with Sabina Schmitz and Omar Abu Abed, and also I was a part of this project, doing for them small angle X-ray scattering measurement. For the second project, lipid nanoparticle in cancer therapy, what we did, we started, this started between Agnes and Sousan Abu Shar. And for the application of the nanoparticle in agriculture and in disease management, which is between me and Rana, and up to now not started, but maybe soon will start it as we got a candidate for this project. The project, it's about carbon nanotube and neural network, and will be started soon as the candidate for this project is chosen, which she's Rama Hindawi. And the last project, which is a PhD project, zinc oxide carbon nanotube, graphene oxide nanocomposites with enhanced anti-cancer activity, will be started in June. And this project is a collaboration between PPU, Polytechnic University Hebron, and IFW Dresden, and between Forschungszentrum Jülich. So the long-term aims of this cluster are applying for a funding to extend and continue our research cluster, develop a new project, and establish also planning for my own research group in Palestine by keeping a connection between the Forschungszentrum and the German universities. Construction, what we also planning for, to build a construction for a simple lab, contain some simple equipment for nanoparticle synthesis, sample preparation, for local characterization, and also advanced characterization will be done by a collaboration with big facilities around the world, like Sesame, DESI, FRM2, and IL, NIST, etc. So, thank you for your attention. And that's all what I have from my side. If anyone have question, please don't hesitate to ask me or type it in chat.
Anyone have any question? Thank you, Asmaa, Dr. Asmaa, for your great efforts.
Okay, so if this is not the case, then if anyone have any question also, feel free to contact me via email. Thank you so much.